Okay, so this is chapter 13, lesson D, where we're going to start covering flux. And we're going to actually start with flux of a two-dimensional vector field, which is really an application that you rarely see, but it's going to connect most to what we did last lesson because it will give us a new type of line integral. So we'll start briefly with that, and then we'll move on to the flux that you normally see, which is like flux of a three-dimensional vector field through a surface. But for right now, imagine we just have a curve here that's just sitting in the xy plane. And then I have some vector field F, and this could represent the velocity of water, this could represent a force, it could represent anything really. We're going to define the flux of this two-dimensional vector field to be the line integral of f, and instead of dotting it with the unit tangent vector like we did last time when we were figuring out work or flow, we're now going to be dotting with a normal vector. And so we're going to define the normal vector here, and then we'll have ds, where we're defining the normal vector as follows. So if I have a curve here, C, the unit normal vector is going to be defined to be the unit tangent vector crossed with K. And in practice, that's going to mean, if this is my unit tangent vector right here, that if you're moving along the curve like an ant or a bug, that you will always be choosing the normal vector that's to your right on the curve instead of your left, because we have two options for choosing the normal vector. And the reason we're doing that is just so that we're all consistent when we talk about positive flux versus negative flux. So in this picture over here, it would be this one that's to the right. Okay, and so an important note, because we've talked about normal vectors before, especially on curves, back in chapter 13. So an important note, the way we're defining this unit normal vector, little n hat, this is not the same as the capital N hat that we defined in chapter 13. That one was the derivative of my unit tangent vector, and that capital N hat could flip where it was on the curve. It was always pointing in the direction that you were turning, or like towards the inside of a curve. And that's different than this little n hat here. So just side note, that's something that can be confusing for students in this class, is we're not talking about the capital N from the T and B frame. We're defining a new little n that will always point to the right of your curve as you're moving along it, and that's going to help us define what we mean by positive versus negative flux. Okay, so we're going to define flux to be the dot product between F and N, and notice as you travel along C, we're choosing the n that is pointing to the right. And for a closed curve, if you are asked to find the flux across a curve, so we can draw something here, it means find the outward flux. That is our default. So if I don't give you an orientation to a closed curve, you can assume it's counterclockwise orientation and that I'm asking for outward flux. Okay, so what is flux giving us? You can notice that since we're looking at the normal component of F along C, in general it's measuring the extent to which F is going across the curve. So instead of last time when we were doing work or flow, the same mathematical computation, we were seeing the extent to which our vector field was going along the curve in the same direction. Now we're measuring the extent to which the vector field is going across the curve. And so if I have, let's just do a generic two-dimensional vector field F here, that is given by Pi and Qj, suppose it was a velocity field. Let's suppose that my units were meters per second. Then let's talk about the units we'll get out of this flux calculation. If F is meters per second, and then I'm dotting it with the unit normal vector, and by making it a unit vector here, I've divided through by its magnitude, so this is unitless. But then ds is going to have units of length. So in this case, we could call it meters. And so you notice we're going to get out something that has units. So this is going to be the flux. We're just thinking about what it means. My units now are going to be meters squared per second. So it's really measuring how much fluid is passing across C in units of area per unit time. Now, in terms of how to actually calculate it, because this is a line integral, we're going to do exactly what we were doing last time when we were doing finding work or flow, which means we're starting by changing variables, and we're going to parameterize to do this, parameterize the curve. And then given that parameterization, we can write out the associated position vector. And then we need to find n in terms of our parameterization. So it's going to be the cross product of our unit tangent vector and k hat, which you recall our unit tangent vector is just the velocity over the speed. And then we're going to cross that with 0, 0, 1. And that's going to give us 1 over the speed. And then times the vector, I will get dy dt. And then my j component is going to be negative dx dt. And the k component will be 0. So this is, we just had to derive this once. This will always be what you use for your unit normal vector. And again, you'll notice that if you are, just to visualize what's happening, if you're moving along the curve here and you draw your unit tangent vector at a given point, which goes in the direction of the curve, and then you cross that, let the k vector just stick out of the page, right, because it's pointing 0, 0, 1, and take the cross product between that orange vector and the vector 0, 0, 1, and you'll notice that your hand is, or your result is going to be pointing here, normal to both the orange vector and the k vector coming out of the page, and it will always be pointing to the right that you're traveling along the curve. Okay, so now we're going to substitute this in to find the overall flux. So we're just changing the variables and calculating what we do. So flux is defined as this line integral, and then we're going to change everything to be in terms of t. So actually let's leave this here because we'll do this in terms of t. And I'm going to rewrite f here, assuming that you've now written it. So f of r of t, just like we did before, dotted with n, which is given by dy dt negative dx dt 0 divided by the speed, and then times ds. So we're going to change ds to be in terms of t, and we know from before that ds becomes my speed times my time here, and then I'd have t going from a to b in this new setup. And so again, we're going to notice that the speed's going to cancel here, and we're just going to be left with this. And we also have a shorthand notation that you'll see, not as many as we had for work and flow, but the most common shorthand notation that you'll see for this is if we, again, let f be given by p of xy, q of xy, then I can replace that up here. I'm not going to write p of t, q of t. You will need to do that. You'll need to change everything to be in terms of t, but I'm just going to write p, assuming you know you've switched it, dy dt, and then I'd have minus q dx dt, just from taking the dot product of those two vectors, and then this whole thing will be dt. So these are equivalent, what I have right here and right here. It's just two different ways of writing it. But the shorthand notation that comes out of this is you'll often see flux just written as the line integral over the curve of just p dy, q dx, pdy minus qdx. And again, this is just shorthand, and it literally means you need to change variables, put everything in terms of t, and actually calculate it like we have above. All right, so let's try an example now.